Chapter 6 is on the real numbers and their representations. And there are 5 sections. The first one is about real numbers, order and absolute value. Then 6.2 is about operations, properties and applications of real numbers. Then the 6.3 is rational numbers and decimal representation. 6.4 focuses on irrational numbers and decimal representation. And then 6.5 is on applications of decimals and percents. So let's get started with section 6.1, real numbers, order and absolute value. So here we have 6 objectives to represent a number on the number line, identify a number as positive, negative, or 0, identify numbers as belonging to one or more sets of numbers, and then given 2 numbers, determine A and B, determine whether A is equal to B, or A is less than B, or A is greater than B. Then number 5 is given a number A, determine its additive inverse and absolute value, and then we're going to interpret signed numbers in tables and using economic and occupational data. I'm sure you've seen this information before, so in a way it's just a review of what you've already learned about the real numbers. They're made up of the natural numbers, beginning at 1, 2, 3, 4, etc. That's a set of natural numbers. When 0 is added to the set of natural numbers, we have the set of whole numbers. So they differ by the number 0. Then the integers are the whole numbers, and the negative or the opposites of the natural numbers. So we go from minus infinity to minus 3, minus 2, minus 1, and 0, and 1, 2, 3, etc. in that direction. Then rational numbers, also known as fractions, are defined as the set of all x such as x is a quotient of 2 integers, in other words, a fraction, with denominator not equal to 0, and that's a set of rational numbers. So in other words, the rational numbers are basically fractions. So we use the set symbolism quite often in the definition of other things as well. For example, in general, we say the set of all x such that x has a certain property. And that is called the set builder notation. We use that from time to time. And so you'll see that again, for sure. Then the irrational numbers, in other words, numbers that are not rational, that's one way of defining it. And there's another way of defining irrational numbers, and we look at that in a little bit. And so the irrational numbers include most roots, like the square root of 3 and 7 and the cube root of 11, etc., minus the square root of 10, and pi. And I'm sure everyone has heard of the number pi, which is the ratio of the circumference to its diameter. So, and then the real numbers is really the union of the rational and irrational numbers. And it's defined, the set of real numbers is the set of all x, such x is a number that can be represented by a point on a number line. And that's a set of real numbers. There's a graphic representation of the set of real numbers, and in fact 2 of them. And so figure 5 illustrates 2 ways to represent the relationship among the various sets of real numbers. And so when you look at the first representation, we look at the rational numbers here on one side, and here's the examples like 4 9s, minus 5 8s, and so on, and the integers that we just discussed a moment ago, and the whole numbers and the natural numbers. So they're kind of nested. In other words, we can say that the integers are a subset of the rational numbers, and the whole numbers are a subset of the integers, and the natural numbers are a subset of the whole numbers. And then there are the irrational numbers. Minus the square root of 7, the square root of 15, square root of 23, so unless it's a perfect square, all square roots are irrational numbers, and similar similar statement works for third roots and other roots. And then pi, the number pi, and pi divided by 4. But what they all have in common that they're real numbers. So the real numbers consist of the rational numbers and the irrational numbers. So that's one way of representing them graphically. Some people like the tree representation in figure 5b. So here we have the real numbers, and so here are the rational numbers and the irrational numbers. And then the rational numbers are subdivided into non-integer rational numbers and integers. And then we have the negative integers and the whole numbers, and then a 0 and the natural numbers. Whatever method you like to use to remember how these various sets relate to each other. My favorite one is really the first one I showed you. To me, it's more intuitive, but again, it all depends on what your preference is. The main thing is that you remember how these various sets relate to one another, and that the set of real numbers is a union of the rational numbers and the irrational numbers. In the first exercise, we list the numbers in the set that belong to each of the set of numbers. So for A, natural numbers, well, there's only one, that's 5. So only 5 is a rational number. For B, whole numbers would be 0 and 5. And C, integers are -5, 0, and 5. So -5, 0, and 5. Then for D, the rational numbers are -5, -2/3, 0, 13 divided by 4, 5, and 5.8, because each one of them can be written as a ratio of two integers. For example, -5 we can write as -10 divided by 2. They're equivalent statements. And 5.8 we can write as 58 divided by 10, etc. So then E asks us for the irrational numbers, and there's only one, that's the square root of 2. And then F asks for what are the real numbers. Well, the real numbers are all numbers in the set. All numbers in the set are real numbers. Now then there's order in the real numbers, and there's a law of trichotomy. And so for any real numbers a and b, one and only one of the following holds true. Either a is equal to b, or a is less than b, or a is greater than b. In the next exercise, we are to determine whether each statement is true or false. So for a, 6 is not equal to 6, that is false, because 6 equals 6. Then for B, 5 is 5 less than 19. So B, 5 less than 19, that is a true statement. And C is 15 less than or equal to 20. So less than or equal, so one of the two can be true, and since 15 is less than 20, the less than applies. So C is true. and 25 is greater than or equal to 30. That is false. Neither the equal or the greater applies. So D is false. And E, here we have 12 is greater than or equal to 12. Well, 12 equals 12, so in this case the equal applies. So therefore E is true. I'm pretty sure you're familiar with these statements here, but if that gives you a little bit of trouble understanding it, then please maybe do some additional drill exercises for section 6.1 to make sure you really understand these concepts. The next topic is that of additive inverses. For example, the numbers 3 and minus 3 are called additive inverses, negatives or opposites of each other. The additive inverse of the number 0 is 0 itself. So graphically, it means that when we have a number line, here in figure 6, and here's 0, and then the distance to 3, of course, is 3, and since distance is always positive, the distance 3 to minus 3 is also 3. But minus 3 is called the opposite because it's opposite from 3. Which explains also the next concept of the double negative rule. For any real number x, the following holds true: minus minus x equals x. And here we can see it in figure 6. So the opposite of 3 is negative 3, and then the opposite of minus 3 would be positive 3. So that's minus minus 3. So that's how the double negative rule can be explained. But you definitely want to remember this one. That will be applied many, many times, so make sure that that's firmly understood. Next, we have formally stated the additive inverse property. That's a plus minus a equals minus a plus a, and that's equal to 0 for all real numbers a. And then we have the idea of absolute value. Again, a concept that you're probably familiar with, but one that will be used many, many times. And that is for any real number x, the absolute value of x is defined as follows. These vertical bars read absolute value of x equals x if x is greater than or equal to 0, and it is minus x if x is less than 0. In other words, the double negative applies in this case. So here we have some exercises simplified by finding the absolute value. So for a, the absolute value of 5 is 5. And going by the definition for b, so it's minus minus 5, so minus minus 5, and that's equal to plus 5, using the double negative approach. Then for C, we know the absolute value is 5, of 5 is 5, but because there's a minus sign here, the answer to C is negative 5. And I can just suggest this, that if this is a bit of a problem for you to understand, really think it through. And you can also go to the book and read up on it there. But it's important to understand how this works. Now, minus for D, minus 14. So we know the absolute value of minus 14 is 14, but then we have a minus sign, so that's equal to minus 14. So this minus sign comes from the one in front of the absolute value symbol. So make sure you don't confuse that with a double negative. That does not apply to absolute value symbols. That only applies to parentheses. And then for E, here we subtract 2 from 8, it would be 6. And the absolute value of 6, of course, is 6. And when we look at f, again, we we calculate what's inside the absolute value symbols. 8 minus 2 is 6. So absolute value of 6 is 6, but there's a minus sign there. So then for f, the answer is -6, because of the minus sign in front of the absolute value symbol. Like parentheses, the absolute value symbols are grouping symbols, but they function differently from parentheses. So here's an application for changes, and the first one is about the population change, and the table shows the estimated percent change in population from 2010 to 2016 for selected metropolitan areas. And here are the various areas in Austin, San Francisco, Chicago, Cleveland, Phoenix, and Detroit. And here's the percent changes for each, or the percent change for each city. And so these data come from the US Census Bureau. And so the question is for A, which metropolitan area has the greatest percent change in estimated population? What is this change? Is it an increase or a decrease? So we look at this, and so we look at the various changes. So what stands out is, of course, that Austin would be the city, or the metropolitan area, Austin. And what is the change? The change is 19.93%. And because it's a positive number, it is an increase. Then the second part of the question is, which metropolitan area has the least estimated change in population? And what is this change? And is it an increase or a decrease? Again, we look at this, and the smallest one would be the Chicago metropolitan area, so Chicago. And the change was 0.35%. And because it's a positive number, this represents an increase. And this is the end of section 6.1.